Here's my presentation for Lab 3, Black Hole and Orbital Dynamic Simulation by Reese Holsworth. Introduction. So for the goal for this lab, we were to analyze the orbital motion of a star around a black hole, and then additionally, as a part two, simulate a spaceship orbiting a planet moon system. The tools we used for this were VPython simulation and Newtonian mechanics. Um, Obviously, there's two parts to this. One was determining black hole mass and creating a complex orbit for the spaceship, the two parts. So physics concepts that we needed to apply for this lab were Newton's second law, force equals dp over dt, and then gravitational force, which is obviously g times big M little m over r squared, and then momentum law, p equals mv. And then we must also understand orbital motion arises from gravitational attraction. On the right, I just showed an example of the gravitational force and how it works. So for system setup, part one, we have the star's mass being given as 2.0 x 10 to the 30 kilograms. The black hole's get at the origin, and the trajectory generated using seeded eclipse data, which we just inserted our username, and that gave us our own. Time to observations was 1 day. Now here is the all the coding I put in for it. I'll show the rest of it later. Okay. Um, so method for finding net force. Um, and a velocity calculated from position data. Momentum is calculated using P equals mv. Change in momentum is obviously just final minus initial, and rate of change dp dt. Net force found using Newton's second law. Force equals mass of acceleration. Whole explanation down here. Estimating the black hole, we use the gravitational law for this. And we solve for the black hole's mass of m, given that we have the star's mass. And then we calculate for each time step and averaged. So as a result, here's a photo of it from the run, from running the data. The estimated black hole mass obtained by got its value, and then the orbit appeared elliptical, and it was consistent with a gravitational two-body motion. Force vectors pointed towards the black hole, obviously, for this. So simulation set part two involving the spaceship. These are all the values taken. Here is the setup for it. Um, yeah, there it is. And then here, I'll just show you the old one. This was just the eclipse going. Yeah. And then for the rocket, it didn't go too far. We didn't do too much. So for submission, obviously we have planet to moon and then spaceship to moon. And on the spaceship was planet on the spaceship, moon on the spaceship, obviously being opposite. And then the collision velocity update was using Newton's second law. The results, as we just said, it finished after 25 point, like a little more than 25 hours. Um, it was kind of just chosen to create like complex orbit, exactly the what they wanted. It showed a multi-body orbit pattern, and then Submission stopped to collide with either, which obviously it ended up colliding with the moon. Um, in conclusion, Newtonian's gravity successfully models orbital motion. Part one allows for the estimation of a black hole's mass using different manipulation of equations. And then part two demonstrated, the multi-body gravitational dynamics that we could use and apply. Showed accurate predictions requiring all gravitational interactions. Thank you for watching.